Hi there, I'm playing with junk again, and this time I have this unit here. It's an AED, an automated external defibrillator. It was in the junk bin because there is no battery. The pads are missing. And I think it has probably some other issues, and well, it's a good opportunity to take it apart. Now we have here Torx with a Torx with a hole in the middle, something like this, security Torx. And a while ago I bought this set of bits here. There are all kind of bits, Torx with a hole, without a hole, this fork-like things. I don't know how this is named. We have tri-wing. They only have 3 wings, of course. I have hex with hole, everything. The problem is, if I use this screwdriver, it doesn't fit into the holes. And that's the problem with most of the units. Whatever you take apart, the screws are always down in a hole like this, and that's completely useless. Now the good thing with Torx with a hole in the middle, you can open it with a normal flat screwdriver. And that works like this. You find a screwdriver where the blade is in a size that you can squeeze it between 2 of the notches here, and you simply open the Torx screw with the flat screwdriver. That's how it works. You see the... Oops, I have to zoom out here. It's not my day today with the camera. Okay. You go in like this, and you have the right size. You can turn it without a problem. Of course, that does only work with screws that are not tightened extremely fast. So, but for this unit here, it works perfectly. And even the screws down here can be opened without the problem. You only need a good quality screwdriver. If the blade is too soft, it will probably bend or break off if it's too hard. So, and it has to have the right size. So fortunately I found one that fits. One's down on the ground, the other one still here. Okay, there it is. 5 on the table, 1 on the ground. Okay, 6 screws. First we have to look at this side here. So here we have the connections for these sticky pads. They go on the patients, one here, one down here, and the heart is somewhere between them, about here. And that's because the current of this unit has to pass the heart to restart it in case if it fails. There is a storage compartment for the pads. There is a magnet, a relatively strong magnet that goes, if you close the lid, there is a magnet switch, a reed switch or something like this underneath the panel here. That means as soon as you open this up, the unit turns on and tells you what to do. It tells you on the display, and it also has a speaker, so this unit will speak to you, hopefully in a language you understand. This one is in German. Then there is another connector here. Looks a little bit like a telephone connector. It maybe is a serial connector or a special shape of an USB. I think that's to for a diagnostic PC to connect that and to set up the unit and check if everything is okay. Oh. This is not a very old unit. Maybe we can find out how old it is. We have here one plug for the speaker. Then we have a second cable. And yes, by the way, this unit is discharged. I have not charged it up, and it was in the junk bin, and it's then stood around for a couple of weeks, and I think there's no danger because there are some quite big capacitors with a dangerous voltage on them. Okay. Yes, that's it. Okay, and that's the big connector here with silicone cables. Very good is insulation. That's what we need because there are a couple of 100 volts or even 1000 volts. Okay, let's see. There's some insulating foam here. What do we have? It's the first time I opened that. There's a big connector which is not connected to anything, so I assume there's probably a daughter board here to, I don't know, maybe some language options, or maybe it's a diagnostic plug for the manufacturing. There are some test points here. Oops, it's a little bit off camera. We have ground, we have 12 volt, 5 volt, 12 battery, -5, reset ground, 5 battery. So the battery provides on this plug here, on these connectors, we have ground, 5 volt and 12 volt, and the serial connection to the battery, so the unit is talking to the battery in some way, or the battery is talking to the unit, I don't know. And then we have two big contacts here. I think that's the main power for charging these capacitors. So, survival link, okay, special capacitors for medical applications perhaps. We have 740 microfarad and 450 volts. The question is, are they all in series or are they in parallel? I think the voltage should be a little bit higher than 450. We have a beeper. which connects here together with this funny indicator here. Oh, okay, that's only a plastic holder of that. Okay, and that's quite a funny little thing. This indicates if the AED is ready. So this is a mechanical disc here that flips over. The other side is green. And as long as it is green, everything is okay. And if it displays red, then you can't use that defibrillator. Let's see if we can hook this up to the power supply. There's some part numbers, nothing about voltage. We have a beeper, okay. It's just like any other beeper. These are other beepers from medical equipment. You know how they sound from all these medical TV series you're always watching. Okay, what's underneath here? Some shielded stuff. I mean, this unit does not only provide an electric shock, it does also measure the heart rate, how it is pumping or not, if it's flickering. So I think all this measurement is very sensitive, so it must be shielded, and perhaps it's in here. That's the chip, Intel ATC186. It's a microcontroller, not the newest model. We have some flash memory here. We have some, I don't know, have to Google that, or maybe you can do it yourself. Some small circuitry that looks like a DC converter or voltage regulator. Then we have some, what is this? Some driver chips, bus drivers or something like that. Don't know. But it looks like they're going directly to this connector here, which is the keyboard or the LCD display. Maybe that's the keyboard, that's the LCD display. Then we have the large unknown connector. We have a small battery. Maybe it's only the battery that is flat and needed a replacement. Who knows? So that's the logic board, and the power board is one floor lower here. Let's see if we can go to that one. Well, just to be on the safe side, I want to go and test these capacitors here, if they really discharge completely. I measure 14 millivolts. I think that's okay. That's about the same. Yes. No charge at all. A couple of millivolts, that's everything. Okay, so we are on the safe side to touch everything. Here we have normal Phillips or PWJ drive screws. Those with the cross in the middle. Some people call them Catholic screws because of the cross. And that one, of course, doesn't come out. There is always one screw that refuses to do what it should. Let's see if a pair of pliers helps. Yes, there is a distance rod underneath that turned with the screw, so there's another connector here which plugs out. There's some more digital stuff here. Not very exciting, just some, what is it? I have to use my magnifiers. 74 AC 373. That's that one. So that's more or less, I think that's a line driver or something. 74 C245. It's that one. Yes, it's good old 74 standard TTL, or maybe now it's CMOS 74 AC is probably the CMOS version of the good old 74 series. So that's the first standoff here that comes out. There's another one. I don't know. It's not necessary to remove them. Okay. Then we also have a lot of foam around here. I think that's mainly because these units are designed to be tossed around. So in an emergency, people normally don't take too much care about this equipment here, so it's meant to work in a rugged environment. Okay, some more screws. Okay, that's the back plate. Some insulation, probably a mylar foil, and some more foam here. Everything is packed together so nothing can move. Also here around these transistors or triacs, I don't know what it is, we have a lot of foam to stop them from moving and probably breaking. So if they move like this one can't move. They are squeezed between, well, they can move. I think that's also a very cost-effective design, as they call it today. In earlier days we would have called this cheap, but well, it works, and most of the time, of course, it hangs on the wall in a box, in a red or in a green box, and waits for, well, to be used. Okay, so let's have a look on this board. One thing, everything is coated here with some silicone coat. It can be scraped away. Yeah, it's just some silicone coat to prevent any moisture, because these units sometimes are located outside or at places where many people are walking around, like shopping centers and so they have to be protected from moisture. There are a lot of these big heavy diodes here. I wonder what they are doing with all these diodes. Survivalink Corporation, that's the manufacturer of the board. So it seems that the company which is printed on the label does not manufacture everything themselves, which is okay. So what do we have here? 3 caps. So 330 microfarad, 450 volts. You can't see how they are connected, but it seems, well, there are traces here to one traces. It seems they are in series, so 3 of them in series, and then we have 4 of those, which are, if you look here, we're going in from the positive here, which is marked. Then we have a link to here, so it looks like they are all in series. We have here pH1 negative, pH1 positive, so the maximum voltage would be 4 times 450 volts, 1600, 700, 1800 volts. Older defibrillators have a bigger capacitor, which is rated for about 2000 volts, and well, I think that's about what it needs to restart a broken heart. That's some sort of, I'd say it's a IGBT or just a big MOSFET. What's the name? Can't see it. Have to look to my glasses. IXBH40N160. That's certainly a high power, high voltage, some sort of transistor. Then what do we have here is CFN 100 478. That could be Triax. So just from the look of the part number, Triax are always a little bit differently named. It's the same. Can't read it. Maybe you can see it on the video here, because the camera, and on the big screen it's always a little bit easier to see. Well, then we have transformer. This is probably the circuit to charge up the capacitors. Then we have here a unit that was shielded. I removed the cover. That looks like some sort of analog amplifier, maybe to monitor the heart rhythm and all this stuff, because monitoring is also done by the sticky electrodes, so it comes in here. So this connections here. On one side they give out the pulse for starting the heart, so a couple of thousand volts, and on the other side they also all the very low impulses from the heart, which is still doing something, comes in here and will be measured down here. So we need, so I think that's some sort of a big resistor. Okay, high voltage resistor. I don't know how they disconnect the sensitive part from the high voltage part, but they are connected together, and maybe there are some opto insulators. Maybe these are doing the trick. I doubt so. So how they are doing this? They're the big, okay, that's the big power lines here. They come from the capacitors and the switching transistors, and they are only thin lines. Yes, they are doing this with these high voltage resistors. So we have here the connectors, the terminals that are bearing these high voltage pulse to the patient, and then they are also measuring the heart rate. These tracks are going down here, doing some stuff around here, yes, and they're going more or less into this box and then up to the logic board that decides if the patient can be shocked or not. There are situations where a shock could be could not do a good thing. Okay, let's play with the indicator. When I'm testing stuff like this, electromechanical parts where I don't know what voltage or current they need, I normally start with 5 volts and limit the current to, in this case, 100 milliamps, so this should be on the safe side. And let's see, I have no idea which one is positive or negative. Yeah, and it flipped to green, and it stays green until I reverse the current, and then I flip it to red. And if I connect it again, nothing happens. So it's just a little disc that flips over from green to red, and in fact it does it in a very funny way. I hope I can show you that a little bit better. So that's green, and now I'm reversing polarity. Ching! Moves to red, and when I reverse polarity again, ching! It flips forth and back a little bit. I think there are some magnets inside because you can't switch them by moving it around, but I think we could hack it maybe with a magnet. Yes, see that? We can turn it around. Yeah, look at this. If I turn the magnet, the disc flips over. And a funny story I heard about displays like this. They are also used in aircraft to indicate some error states. For example, if something is wrong with an electric circuit. Oh, I hope I did not damage it with my strong magnet here. And some of the technicians, instead of repairing the defect, which is indicated by these lights, now okay, it's here again, they just take a little magnet and turn this from red to green, or from yellow to black, or whatever the colors they used, and think it is repaired then. Well, of course it is not repaired, but the error indicator doesn't show the error again. And if it stays like this, it's okay, and if the problem comes back, they actually have to repair it. Well, that's not common practice, of course. Well, I hope so. But I heard this from a colleague who worked in this aircraft business, and he told me that one day a guy came in and asked for a magnet, and when they asked him, why do you need a magnet? They told him that he uses them to reset these indicators. Well, that's probably not the way you should do it. Okay, one thing I always like is this sort of beeper here. There's no indication, it's just a OBO 35D1. I'm sure we could Google that, but I just want to know how it sounds. So I do the same as with the indicator. I set my power supply to 5 volts. In this case I think red is positive, black is negative, which would be logical, except it is a Chinese product where sometimes the colors are the other way around. Power on. Ooh, nice. The two-tone beeper. Let's see how much current it draws. Maybe we could make some annoying toy with a battery. Yeah, 8 milliamps at 5 volts. That means with a small battery this would annoy people for a very, very long time. Now, as I already told you, I have 3 more of these beepers. I connected them in parallel. That means we'll need a little bit more current. I set the limit to 1 amp and I keep the 5 volts. I hope blue is negative. Let's see how 3 of them sound. I think the voltage is too low. These are, I think, designed for 12 volt. Ooh. I don't know if the camera microphone can pick that up correctly, but it's incredibly loud, and because these 3 beepers don't have exactly the same frequency, you can hear well, how do you say that in English? A mixture of the 3 frequencies, which is even more annoying. Okay, I think that's it. Thanks for watching.